Welcome to Lesson 8C, Gaussian Puff Model, Absorbing Ground. We're going to spend a few lessons on Gaussian puffs. We're going to start with an absorbing ground, since it's easiest. What is a Gaussian puff? Well, we'll do a model which applies to things such as explosions, building demolitions, sudden release of a gas, a burst tank, a tank that contains a gas that bursts suddenly, anything that's a sudden burst of an air pollutant. And this happens at t equals 0. So at t equals 0, we have this sudden explosion that releases some gas. And the explosion occurs at some height h off the ground. This ground is absorbing. The main difference here between the plume and what we are now talking about, this puff, is that this is now unsteady. So there's a little bit more level of complication here. You can visualize what happens if I plot z versus x. So it's just looking from the side view. There's this explosion at t equals 0. And then this puff, we call that a puff then, of smoke or gas, whatever's coming out of this explosion, that's the air pollutant, is moving downstream at some speed u. It's moving downwind. And this puff, if you imagine a cloud of smoke or gas, it diffuses. So as you go downstream, it is diffusing out and getting bigger and bigger. Now, I drew it purposely not round because it's not necessary that it be diffusing the same in the x and z directions. In fact, the z direction, we know that the diffusion is greatly influenced by atmospheric conditions. And to some extent, the horizontal one is too, but this vertical diffusion can be much different than the horizontal diffusion. So this thing keeps moving down. It gets bigger as it goes. Now, when you get to a certain location and this part of the puff, now this is a puff that keeps moving downstream and growing. Since it's an absorbing ground, that part is gone. It is in the ground. Say if it's smoke particles, those particles, as soon as they hit the ground, they're absorbed by the ground. They just sit there. Some gases get absorbed by the ground as well. And so if you are standing here and you're breathing this puff, what do you see or what do you sense? Well, this is a Gaussian and it's a Gaussian model. So if I plot, in this case, Cj as a function of x, but remember this is also a function of time. So this is changing with time, but at this particular time downwind, I have a Gaussian that will look something like that. I also can plot Cj, I'll just use a different color here, Cj as a function of direction z, and that will also be a Gaussian, and that's going to look something like this. So we have a Gaussian vertically and a Gaussian horizontally in the x direction. We also have one in the y direction, which I'm not showing here, but I'll show below. Now, where does this happen? This is a puff that's moving. It's unsteady. And so let's define this location. If this location is x1, what is x1? Well, x1 is t1 times u. So at some time t1, the center of the puff has reached distance x1. And you can also do the same thing for other x's. So this is x2 is equal to t2u, etc. And so in general, we can write x equal tu as a kind of transformation between time and space. So this was a side view. I can also plot a time plot. So now I'm plotting Cj as a function of time, where I was plotting Cj as these circles. But now, what does it look like in time? Well, at 0, at time t equals 0, what do we have? We have this infinite spike of mass, where all the mass is released at time t equals 0. This will be time t1 that corresponds to this x1 we had up here. So I just went straight down. What will it look like there? Well, it'll be a Gaussian that'll look something like this. So this infinite spike is infinitesimally thin, but it's infinitely tall. Now it has spread out. It's gotten a little fatter and shorter. And then this keeps happening. It gets more wide, fatter, and it gets shorter as we go downwind or as we move along in time in this case. So this is T3, T4. That's what's happening. And so for our particular person, if this is you and you're standing there and there was this explosion and you're directly downwind, of course, there'll be some Gaussian in the y direction as well. But if you're directly downwind, what will you sense? What will you feel? What will you breathe? Well, you can see by both of these diagrams that at time t equals 0, there's the explosion. You don't feel anything. So the puff is moving its way downwind. You don't feel anything until the front of the puff hits you. And so what you experience is actually a Gaussian. So you have nothing for all this time. And then suddenly at time a little bit less than t3, because t3 is when it's centered, you start sensing this contaminant, it reaches a peak right when this puff is directly centered around you, and then it starts to fall again. And then after that, after it's gone, it's way down here. This person will be feeling it, but you don't feel it anymore. So what you feel is that puff just come for a short time and then leave. And so it's the total dose that you need. It's just an integral of this whole thing that we're interested in, that it tells you how much of the contaminant that you've breathed or you've been exposed to. Sometimes this is skin damage if it's a gas that hurts your skin, etc. It could be breathing or some other problem. Now, let's look also at the top view. From the top view, here's the source. We're going to call this MJ for the source, and this is a mass that's released, not a mass flow rate, it's a mass. Now we're plotting X and Y axes, and you can see that from the top, we expect the diffusion to be the same in any horizontal direction, so the wind just happens to be blowing, but if this puff moves with the wind, it doesn't matter if you're talking about X or Y or some 45-degree line. We expect these from the top view to be perfect circles in this model. And nothing's ever going to be a perfect circle, but it's a perfect circle in this model. And there also is a Gaussian distribution in any direction. So if we, again, plot our Gaussian, it'll look like that. I can also plot it in the X direction. I can plot it in a 45-degree direction. It's going to be the same in any direction because it's diffusing. That'll be important because it'll turn out that the diffusion coefficients in the Y and the X directions will be identical. So what we're going to talk about is the integral of this, which we're going to call the dose. But before I do that, I want to show you a couple videos that I got from YouTube to illustrate these puffs. The first one is a building implosion. These are really fun to watch when they purposely tear down buildings by putting explosives in. And you could see the big dust cloud that appears. Unfortunately, when they take these videos, they never watch the dust move along after it's done. As soon as the buildings collapse, they shut their camera off. But they always try to do this when the wind is very calm or there's hardly any wind at all, so that all that dust and everything just settles down and doesn't drift. But the second video is of a smokestack demolition, and that one there was some wind, and they should not have ever done that with that much wind. And I'll mention in the video there were lawsuits and everything. So let's do that video now. Here's a really cool video that I found on YouTube. If you look at the top left, you can type in the title to watch the actual YouTube video. But I'm recording it here in voice narration over it. You can see that a smokestack collapsed, and then there's a big puff of dust that was generated by this controlled implosion, demolition of that smokestack. And there was also wind that day. They usually try to do this on days that aren't very windy, but in this case, there was this dust cloud that swept downwind onto a town, and there were lots of lawsuits and everything. You can read about it some more if you want, but this was a very cool video, good footage, where you can see this dust cloud just moving with the wind. The wind is actually pretty high, so you can't really observe much diffusion here, but this cloud, it's not very round either, but you can see that what we're doing is just an approximation of a puff like this, and then depending on the rate of diffusion in the X, Y, and Z directions, you can get something that's pretty spread out like this, or you can get something more circular. So this is a pretty cool video, I thought. Okay, how do we analyze this Gaussian puff diffusion model? Well, I am not going to go through all the algebra. This is very similar to what we did for the Gaussian plume, except now it's unsteady. But notice we have this x minus ut here, where we use that coordinate transformation, as I had mentioned, since x and t transform to each other by x equal tu. So if put in x minus ut, you're effectively moving with the puff. So it's kind of like when we do the same thing with the height, we take z minus minus h instead of just z, so that you're accounting for the height above the ground. Well, here we're accounting for the time as this puff moves along. So this is really just a solution, which, remember, the squiggly line means lots of math involved here, but this is your final expression. I'm not going to go through all the derivation. Notice again, there's a total mass that's released. That's what we'll call mj. And then there are these diffusion coefficients. I put another subscript I, so we have a sigma xi, sigma yi, sigma zi. However, sigma xi and sigma yi are the same, and that's because of these circles here. So it's diffusing exactly the same in any horizontal direction. It turns out that sigma xi and sigma yi are both equal to axb, and then sigma zi is equal to cx to the d. And let me make some comments here. Number one, we use x minus ut up here in place of x to account for the puff moving downwind at speed u. Number two, diffusion in x is not neglected here. We are keeping this diffusion term in the x direction, unlike what we did for Gaussian boom. In that case, the convection or advection with u was dominant over diffusion in the x direction, but here that is not the case. Sigma xi, sigma yi, and sigma zi are instantaneous diffusion coefficients, hence this extra subscript I for instantaneous. These are not the same as the Gaussian plume ones that we had already talked about before. We're going to use a different model to calculate these instantaneous diffusion coefficients, so you don't use the same ones that we use for the Gaussian plume. And then finally, number 5, as I already had mentioned up here in our equation itself, sigma xi and sigma yi are the same because diffusion in any horizontal direction is the same. So what we need to do is calculate these instantaneous diffusion coefficients, and then we'll be set to go. We can do some examples. Now, there's something very confusing that I don't like, but this is how it is with these engineering equations. These sigmas are in units of meters, as the old ones were, but x is now also in units of meters, not kilometers. So remember, for the Gaussian plume, you'd keep x in kilometers, and you'd plug in for the sigma y, it was ax to the b, just like it is up here. But it turns out that you'd use x in kilometers, and then sigma turned out to be meters. Here, these instantaneous ones are again in units of meters, but you keep x in meters, not kilometers. So make sure you don't make that mistake. The good news is that there's a very simple model, much simpler than the other one we had, and this is called the Slade model. That's the one we're going to use. That's the simplest one. There's only 3 stability conditions for the atmosphere. Remember, we had A, B, C. We also had A-B, B-C. So we had all these different types of stability condition depending on the sun, how high it was from the horizon, how many clouds there were, all that stuff. Now, they just use 3 very simple ones: unstable, neutral, and very stable. So obviously this is getting more stable as you go down this way. Other nice thing is there's only 4 coefficients. We also had an F here that is no longer there. So we don't need an F anymore because our equations are up here. We just have sigma xi and sigma yi are a to the xb, and sigma zi is cx to the d. So my comments are only 3 classes: unstable, neutral, and very stable. Only 4 coefficients. We have no F in these equations, and I'll have to give you the class. I can't just say it's sunny because there's no details like that. All we have here are these 3 classes, so I will have to give you that at any kind of problem that we do. All right, I mentioned dose. If you're standing at some location XYZ, what is your total exposure or dose? We define this DJ as the total dose of species J at some location XYZ. So DJ is a function of XYZ, and how do we get it? We integrate over time. We're going to integrate CJ dt, and notice that CJ itself is a function of X, Y, Z, and T now. We saw that in our equation 1. We're going to have to integrate this guy to get the total dose. And we integrate from t equals 0 to infinity of CJ times dt. We integrate from 0 to infinity because when you're actually doing this integral, you're going to have a whole bunch of time where nothing's happening, and then you get your dose, and then from then on you get nothing else. So we go from 0 to infinity, but the actual dose occurs within a short period of time. I always like to look at dimensions and units. Integral of CJ dt, so CJ is mass per volume, and then when you integrate with time, you get a time there. So the dimensions are m over L cubed times t, and the units typically are milligram second per meter cubed. So we need to integrate, and I'll do my curly arrow. This would be good for a long, cold, rainy night if you have nothing better to do. You can integrate this. And this is our final answer. I call this 2A, the A for absorbing. And so this is the equation for dose of species J for an absorbing ground, Gaussian puff diffusion. So it reduces kind of nicely. It looks very similar to what we had for the Gaussian plume. And we've lost time because we've integrated over time. And you say, well, we lost X too. What happened to the X? Remember, we had an X minus UT in our equation. Well, when you integrate, the X actually drops out. So does the sigma xi, because that's the same as sigma yi, and that drops out when you integrate as well. And so we get this expression. So now let's do an example Gaussian puff diffusion. Here we have a ground level tank containing 10 kilograms of hydrogen cyanide. So let's label some of the things. Ground level tank, that means that H is equal to 0. And 10 kilograms is your total M. Mj, that's the mass that's released of this nasty gas, hydrogen cyanide. The tank ruptures and it leaks this gas in a big puff. The atmosphere is stable and there's a gentle breeze blowing at 1.5 meters per second. The ground absorbs the HCN on contact, which means we can use equation 2A here. Workers downwind of the explosion are exposed to this HCN. So part A, we want to estimate the dose of HCN that would constitute hazardous conditions for the workers. So what's the maximum safe dose, DJ max, in these units that I told you, milligrams second per meter cubed? Well, this is not the same as the previous problems where we had a steady situation and we look at the PEL. Here, we look at our NIOSH pocket guide. Here, the more appropriate level is the STEL, or the ST as they call it on the NIOSH pocket guide. This STEL is the maximum 15-minute exposure level, so it's a short term. In fact, this means short-term exposure level. The PEL is not appropriate because that's for 8 hours of exposure. Here, you're just exposed for a couple minutes. So we want to look at this total dose over a short time. So you can look that up. The ST or STEL for HCN turns out to be 5 milligram per meter cubed. So the safe dose, we can also call it the max dose or the hazardous dose. These all are interchangeable. We're looking at the limit would be 15 minutes times the short-term exposure level. So here we can do the math. So DJ safe is 5 milligram per meter cubed times 15 minutes times unity conversion factor, 60 seconds per minute. That gives us 4,500 milligram seconds per meter cubed as our safe limit. So what we're really doing is taking this area, which is ST and 15 minutes, and equating it to the actual area that we're exposed to, which is the area under the Gaussian. So if we equate these areas, that's effectively what we're doing to calculate this safe dose. Part B is to predict the ground level dose directly downwind at X equal 1.5 kilometers. So ground level means Z equals 0, directly downwind means Y equals 0, and we're given X. Here's the parameters and conditions, a summary. Very stable atmosphere, so we know which one to use in this SLADE model. Very stable. Wind speed is given, that's our U. Total mass is our MJ, and the explosion is at ground level, so that tells us that H equals 0. So the rest is somewhat similar to what we did for plumes. We just look at our model, get our coefficients, so we're going to use these coefficients here, and we calculate our sigmas. Now be careful here. When we plug in X, we use X in meters, not kilometers. For the past couple weeks, we've always been using kilometers for X when we calculate these sigmas, and now we're using meters. So that gets a little confusing, and I apologize for that, but that's how these are set up. So we have our sigmas, and now we need to just plug into this equation. In our particular case, we have at Y equals 0 and Z equals 0 ground level, and H equals 0. The tank was on the ground. So this is 0, this is 0, this is 0. So this whole thing, we have this EXP of 0, so that's equal to 1. And so this whole expression becomes DJ, for our particular case, is just all the constants in front. So I plugged in all our numbers and used a 1 unit conversion here. And so we get our final answer to 3 digits as 36500 milligrams second per meter cubed. This is the dose that's received or felt or encountered by the worker at this particular location. Now remember, from part A, our maximum safe dose was 4,500 same units. So this far exceeds the 4,500 safe limit. So this is indeed a hazardous dose for that particular workman. All right, part C, let's repeat at various x locations. You just repeat this for various x's, have to calculate the new sigma yi and sigma zi for each x. And let's look at that plot compared to the hazardous dose. So this is the maximum safe dose in this dashed green line. So everything above here is considered hazardous. Everything below is considered safe. So we see that up to about 6 kilometers, everything here is hazardous and everything here is considered safe. So everybody directly downwind of the explosion is exposed to a hazardous dose up to about 6 kilometers. Now you can also plot a hazardous area. How do you do that? You solve equation 2a for y, and you've done this numerous times, and it's exactly the same kind of algebra. In fact, we get a very similar looking equation, which I'm going to just write this way and have you do that on your own. We get a plus or minus sigma y. This is now a sigma yi, -2 natural log of a bunch of stuff from the equation. So you can solve for that like you've been doing, and then plot the hazardous area downwind of the plume. And once again, we expect some kind of a ellipse looking thing. That's the hazardous area. In this case, it extends all the way to 6 kilometers. But notice that it starts right at 0, and that's because this thing is right on the ground, so anyone very close to the explosion receives a hazardous dose. If H were bigger than 0, the explosion's up on a platform of some kind, we'd expect this hazardous area to shift downwind and also be a little bit less in area, because the higher up the explosion, the more time it has had to diffuse. So if there's an explosion way up in the sky with a wind like this, you would expect the hazardous area to be much smaller, or perhaps even non-existent, when you have all that time to diffuse.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.